particle accelerator facilities, of course, we all are very familiar with the operations of accelerators and the use cases and things like that. One of the main motivations is trying to optimize the amount, how the accelerator time is being used. So I tried to categorize it into three sort of high level categories. We have just R&D time, which is running experiments for machine development, beam experiment time, this is serving the end users, and then sort of the much undesired downtime. And usually either scheduled maintenance or unscheduled maintenance. I think for anomaly detection, at least for me, the most interesting thing is trying to mitigate unscheduled maintenance, and then also trying to have a better sort of understanding of of optimizing the use of scheduled maintenance. And I'll talk a little bit about what I mean by optimizing the use of scheduled maintenance in one of the examples, but essentially we're sort of interested in minimizing downtime so that we can optimize the amount of time for R&D and for experimentalists. So there's, in machine learning, we have the two broad categories that are sort of, there's a lot of work being done in the field in this, obviously, supervised learning and unsupervised learning. And usually talk about supervised learning in cases where you know what the inputs are and you know what the outputs are. So surrogate modeling, for example, convolutional neural networks as classifiers of images, things like that fall very cleanly into supervised learning. And then in unsupervised learning, you don't have any idea what the labels are. For example, in some anomaly detection cases, you don't know what the faults are, or you don't know what is considered anomalous. A really nice example of machine learning for unsupervised learning is using autoencoders to detect credit card fraud. So this is a case where you train an autoencoder on what is considered to be normal credit card transactions, and then you flag any credit card transactions that fail to the reconstruction test for the autoencoder. And this is sort of the simplest use of autoencoders for anomaly detection. There's a few other ones. I'm going to touch on two different methods in this presentation. One is the reconstruction test, and the other one is latent space analysis, which I'll talk a little bit about next. So what is an autoencoder? I like to think of an autoencoder as essentially a identity transformation for a given data set, but it's a nonlinear identity transformation that also includes this dimensionality reduction in the middle. So in the examples that I'm looking at here, it's all just standard feed-forward neural networks where we reduce the dimensionality of the layers down to some minimum, which we refer to as the latent space, and then we reconstruct the information in the decoder section, which is essentially the inverse of the encoder section, and you train it to basically reproduce a data set. So the two different things we look at are just latent space analysis, which is you train an autoencoder on a given data set, and then you say, okay, I want to study the compressed representation of the data set. And you could do this for a few different reasons. I mean, in one case, maybe you want to just simplify or reduce the dimensionality of a given data set, and then you want to use that as inputs to training a regular supervised learning neural network. Or maybe you want to study the latent space and look for anomalies, and the latent space gives you a smaller dimensionality, so it's easier to do clustering or easier to do other types of sort of anomaly detection tasks just on the latent space as opposed to on the raw data set. In the example I'm going to look at today, we're mainly interested in just looking at the latent space and looking for sort of anomalies or clustering or things like that that are more present in the latent space than you might get by just analyzing the raw data. And then the reconstruction test is sort of the other thing that I'm looking at, and that's you basically train the autoencoder and then you test the autoencoder on some unknown data, whether that's data that's outside of your training set or whether it's just validation data or whatever it is. This is sort of the testing of whether or not your data is anomalous or not. And you can look at the degree to which individual parameters fail to be reconstructed, or you can look at aggregate parameters. For example, the RMS reconstruction error is a single aggregate parameter. And this is pretty useful if you're thinking about how to take this into an operational setting. and you have dozens of machine parameters, and you want to understand whether or not the machine's entered a different state or an anomalous state, you now have one metric that tells you about what the machine's doing relative to past states, as opposed to having to look at 12 different metrics. And the same is true with the latent space analysis, where you can look at instead of having a dozen metrics, you say, oh, we only have 2 or 3 latent space parameters that we can look at. And that's a little bit easier to digest from an operator standpoint. So in terms of trying to bring these into operations, I think these are 2 areas where you can really reduce the amount of information that has to be analyzed on the fly by operators. So I'm looking at 2 different case studies today. The first case study is an analysis of some RF data on the Fermilab low energy LINAC, and this is a relatively simple case study. There's only 10 input parameters, and we're looking at both reconstruction tests and also latent space analysis. And then the second example is looking at just reconstruction tests, and that's in magnet faults in the APS storage ring. So this has many more parameters. It's a much more complicated problem, and I'll show some results from both of these studies. So just to orient yourself to the Fermilab accelerator complex, if you're not familiar, there's the LINAC, which accelerates protons to 400 MeV, and then those are injected into the booster, and the booster accelerates them to 8 GeV, which goes into the main injector or the recycler or anywhere else in the accelerator complex. But the LINAC is sort of the main machine that feeds the whole accelerator complex right now. And inside the LINAC, there are 4 sort of primary subsystems. There's the ion source, there's the RFQ, the drift tube LINAC sections, and then the coupled cavity LINAC sections. And for the purposes of this study, I focused on the drift tube LINAC section, which is broken down into 5 tanks. And each tank is independently controlled with RF klystron, and that has amplitude and phase information. There's beam current measurements that come out of each one of the tanks, and then there are also beam loss monitors along the LINAC. For the study, for this particular study, I didn't look at the beam loss monitors. It's something that we could do in the future, but I was mainly interested in trying to correlate or not changes in the RF parameters with changes in the beam current measured at the end of the LINAC or even along the LINAC. And on the bottom here, I'm showing a plot of the beam current as a function of time during the study. So this is a retrospective study looking at 20 weeks of data taken during the 2019 to 2020 run. And there's sort of 3 more or less operational modes. I don't want to call them modes, but just sort of 3 regions in the data set. There's the tune-up region. This is during the initial startup of the run, and there's a lot of parameters that are changing. You can see that the beam current is changing quite a bit, and there's areas of downtime where things are happening or they're not running the machine full time. And then there's this stable operation period, which is during basically the beam current and the RF parameters and all of the parameters that we're looking at are relatively stable. I mean, there's obviously some fluctuation, but more or less things aren't changing a whole lot. And then there is a third region, which I'm referring to as the reduced output region. And this is towards the end of the study period where the beam current is reduced by an amount. And I'll show later sort of that it doesn't just step down, it does sort of follow there's a little bit of a decay in the current. But the main thing I was trying to understand is what is the root cause of this reduced output in the beam current? And can we point to an RF related change that would have led to this change in the output current? And I think the next few slides, I'm going to talk about the 2 different studies that we did to try to understand that and sort of the takeaways from those studies. So the first thing I want to just orient a little bit more to the data set. So I was showing the full 20 weeks before. This is zooming in starting at week 5. So if we remove the first 5 weeks of sort of tune up and accelerator turn on time, and then just look at what happens during weeks 5 through weeks 14 or 15, and then what happens after that leading up to the end of week 20, which is the end of the data set. So you can see on the left, this is the beam current output at the 5 different toroids along the LINAC. Obviously, not all the toroids are calibrated to the same level because the toroid at the end of tank 3 is showing a lower current than the toroid at the end of tank 5, which is kind of impossible. So obviously there's some difference in the calibrations here, but for the purposes of this study, that's not necessarily that important. What is more important is that there's a sharp change in the current right around week 14, and then there's a decay in that current, and then it sort of settles out to some other value that's not the original steady state value during normal operation between weeks 5 and 13. And the question that I was interested in trying to answer was, is this related to changes in the RF parameters? Or was there a change in the RF system that caused this, and then there was retuning that then caused the system to settle out at some other value? And just for a little bit of background, my experience working with RF systems in a couple of different LINACs is that sometimes calibration parameters change, or there's a small cable that's inserted, or there's something happens to change a phase, or maybe something happens that's not documented, and that changes the meaning of the settings that are being manipulated in the control room. And if this isn't properly accounted for or documented, then that could cause you to be operating with RF settings that don't mean the same thing as they did maybe 2 weeks before. So my initial thinking was, oh, I wonder if that's going on here, and if it is, can we use autoencoders to try to answer that question? And the first thing, so when you talk about autoencoders and simplifying the data set, autoencoder is relatively complex compared to a number of other simplification methods. If you have a LINAC, you could just start by doing a vector decomposition of all the RF signals into the in-phasing quadrature components. And then you could sum these up and say, okay, I have 2 parameters that tell me what the RF system is doing for the 5 cavities. It's the I and Q component, the vector components of the RF system. And if they're changing, then that's going to tell me that there's something that's changing in the RF system. We looked at that, and so I'm showing in the middle here, I'm showing the fractional change in the I and Q components of the RF cavity as a function of time. And it's fractional change, so this is on the order of, these are basically fractions of 1% to 1% or so change. And to compute the fraction, I'm using the median value of the parameters across the whole study. And you see that for the I and Q components, the changes are on the order of 1% or so. And while certainly it does settle out to some value that's not really quite where it started at, it's not a very big change compared to the change in the beam current, which is on the order of 10 to 15% or so change in the output current. So if you were just looking at this, you might say, okay, the RF's not doing anything weird. There's certainly changing, but it's not obvious that there's a direct correlation between the RF change and the beam current change. And then also looking at singular value decomposition. So can we just do a linear SVD to extract more information from the RF states than we're getting from just the IQ decomposition? So here you're looking at an aggregate of the 10 singular values. This is because when you do the SVD, they're all sort of different scales, and you don't want the metric to be more sensitive to one singular value than the other. So I just rescaled all of them to be on the same scale and then aggregated over them. And now you're looking at the variation in the singular values as a function of time. And again, there's not a whole lot of information coming out of that. And it would also suggest that perhaps the RF system is not really related. Changes in the RF system aren't really related to changes in the current, especially just qualitatively looking at these two plots. They don't really seem that similar. So I did an autoencoder study on the RF parameters, and for this study, I did not include the LINAC current measurements. This is just on the RF parameters, the amplitude and phase measurements, and trained a few different architectures of autoencoder. This is just one of the ones that we ended up with, and examined the architectures with different latent space dimensions. So you can pick whatever you want. I mean, the simplest one is obviously have one node as a latent space and the more nodes you have with latent space, then the easier it's going to be to learn. And theoretically, if you have equal number of latent space nodes as you have parameters, then you're just going to learn basically identity transformation, and it's essentially trivial. So that's sort of the bounds of your latent space dimension. And what we saw is that when we did a test over 10 random initializations, if we trained the neural net with latent space of 1, 2, or 3, that when we went from 1 to 2 nodes, the error on the training and validation set went way down. And then when we went up to 3 nodes, we saw an improvement, but it was a marginal improvement as compared with going from 1 to 2. So that sort of says that 2 is adequate, 3 is better, but obviously if you just keep going up, it's going to sort of turn into a trivial problem. And then we also did some analysis of the reconstruction and just looking at how well it performed on 2 versus 3 encoded dimensions, and it just didn't make a huge difference. So we stopped at 2. We said 2 is the simplest that has some significant improvement over 1, and then we'll just go with that. And then the next thing is to look at the output of the latent space as a function of time and see if that relates to the change in the current. And here I'm showing that for 2 different examples. So these are 2 different randomly initialized autoencoders. So that's why you're seeing such different fluctuations between the top and the bottom. And the point I'm interested in is at the end of the study, does the final latent space look anything, does the difference between the initial and final latent space at all look similar or correlate to the difference between the initial and final latent space, or the initial and final output current? And somewhat, I mean, so then also compare this to the sort of more basic analysis of looking at just the I and Q decompositions. So for the I and Q decompositions compared to the latent space analysis, there's obviously similar changes. So I've highlighted areas where there is a change in the I and Q, and there's also a change in the latent space. So we're seeing that there, but there are much larger changes in the latent space. So the fractional change is closer to 1 as opposed to being 0.01, which is indicating that there is maybe more going on than is visible by just doing the IQ decomposition. And it's suggestive that perhaps there is something going on in the RF system that might be important to look at. Right, and I don't have the plot that shows the change in the output current right next to the change in the latent space. What I will say about this is that the results are suggestive. So it highlights that there is perhaps more going on in the RF system than is immediately obvious by some of these more conventional techniques. Unfortunately, we don't have access to there's no logged change in the RF system that would correlate to what I was talking about before would be a calibration shift or something like that. So this is a little bit anticlimactic and kind of frustrating from a study standpoint. But I think that the main takeaway is that the latent space analysis can potentially tell you a lot more about what's going on in your system and give you things to look at that might be of interest in the future. So I think it's something that we're still interested in and still working on, but in terms of this particular study, we sort of didn't have a whole lot more to go off of. If you look at the correlations between the latent space and the changing current, there is a weak correlation. It's a little bit stronger than the correlation between the change in the I and Q components and the change in the current, but it's not so strong that it's more than just a suggestive result. So there's probably something else going on. There's probably something going on in the RF system. There's probably also something going on upstream of that we just don't have any information about. But I think for us taking this forward, we're sort of interested in using these techniques for other types of problems. And then the other thing was autoencoder reconstruction. So I talked about this earlier. You train the data over some period, and then you say this is normal, and then you test it on some period that it wasn't seen during training and say, how does this data fail the reconstruction tests? Or does it fail the reconstruction tests? So there's 2 different studies from the RF data, and I want to get to the magnet study next because that's a little bit more interesting, but also I'll breeze through some of this a little bit quickly. Basically, we said 5 or 15 or 10 weeks of training, and then we'll test on the other data and see how well the reconstruction error, look at the reconstruction as a function of time and see if there's a significant shift. And then this is just the same sort of convergence study on the number of nodes in the autoencoder. Since you're looking at reconstruction, you're not as limited. You could have more nodes. It's not like you could say, oh, RMS reconstruction error is a single aggregate parameter, so you don't have to stop at 2 or 3 nodes. We do see a slight improvement when we go to 4 nodes, and then 5 nodes, we start to see some overfitting. So kind of stick to 4 for some of these studies. And then this is just showing the reconstruction error as a function of time. And for the case where we have 5 weeks of training and then 10 weeks of testing, and you see that it obviously it does very well. The reconstruction error is quite low for the first 5 weeks, and then it starts to change, and then there's a significant offset in the last few weeks that's different than the first few weeks. And naively, you could say, oh, well, the RF parameters just changed. I mean, if you go back to the previous slide, these are just very different than here. And if we're just training on this, then sure, the neural network's not going to learn anything to be able to reconstruct this. The interesting thing, though, is when we go to a larger training and validation set, we have very similar offsets in the test set, even when we are doing a good job of reconstructing the data all the way up through weeks 17. And when we overlay them, I think it's pretty interesting that the reconstruction error is almost identical for all of the cases, whether we're training or training on 5 weeks or 10 weeks of data. So I think this is also suggestive. Again, when you look at the correlations between the RF parameters and the beam current and look at the correlation between the reconstruction error and the beam current, the reconstruction error is more strongly correlated with the beam current than the RF parameters are, but unfortunately it wasn't by an overwhelming amount. It was like 5 to 8% more correlated. So it's again suggestive that there's something going on there, but either a different study is needed or more information is needed about other parameters or other things. But I think that the main takeaway on this study was just that, oh, this is encouraging and showing some stuff, and it's kind of interesting. Yeah, and I'm not going to stay on this slide. I'm just going to go on to the next thing. Okay, so the next thing that we're looking at, and this is, I think, a little bit more compelling, is we want to try to detect faulty magnet power supplies in the APS storage ring. And there's 2 questions. The first question is, can we simply predict if a fault's going to occur? And the second question is, if we can predict if a fault's going to occur, which magnet is it that will fault? And can we say at what time will it fault? So this is trying to get to the trying to do better planning for planned maintenance. So you say, oh, well, this magnet will probably fail within a week. Then you can say, instead of waiting for it to fail, you can replace the power supply sooner, and then you don't have to have unscheduled downtime, which is pretty important for the light source users. And then also just being able to say, oh, we think a fault's going to occur at some point in the next 10 minutes, then that would encourage users to finish up their study or prepare for the fact that they're going to have beam loss, so they're not caught off guard by that. So just to orient to the problem here a little bit, this is a schematic of the storage ring. The storage ring has 40 different sectors, and there's A and B sectors for sort of each of the 40 sectors. And there's quadrupole sectables, correctors, and then also the dipole magnets, of course. In this study, we're not including data from the dipole magnets. We don't have fault data on those. We just have fault data on the quadrupoles, the sextupoles, and the corrector magnets. And for the study, we have time series data for all 1,320 magnets. We have power supply temperature, we have magnet current, we have magnet temperature. For some of the magnets, we have additional diagnostics, but we don't have the same diagnostics for all the magnets. So if we're going to look at data for the entire ring, then we just limit it to just looking at the temperature or just looking at the power supply capacitor temperature. And there's two types of data that we have. We have what we call reference data. Reference data is collected, basically they're in the vicinity of no faults. So it's some period of time before any fault occurs. It's considered normal operation. It's the quote unquote reference data. And then the test data is data that's taken leading up to a fault, but the actual fault that occurs is not in the data set. And even the few seconds leading up to the magnet failure, we don't have that data. I mean, it exists, but we don't, for the purposes of the study, we're not including that because we want to try to see if there are precursors that are detectable outside of that. And we have the labels for many of the data. So we do know for a particular set of runs, oh, this is the magnet that failed. And we do have that information. So we can do some supervised learning, but we have a ton of data during normal operation. So to me, it seems like a good candidate for unsupervised learning where you say, let's just learn what normal is and let's flag what we think abnormal is and see if our abnormal flags are correct. And there's a couple of simplifications we wanted to do. So 1320 is, obviously that's not a crazy amount of inputs and outputs for a neural net, but it is relatively large. And I thought it would be interesting to just say, okay, can we simplify the problem a little bit and just have fewer parameters? I applied two different simplifications. One is aggregating by the sector. So there's essentially 80 sectors, 40 A and B sectors. So now you have 80 inputs and outputs. And then the other thing was, can you aggregate by a magnet type in a sector? So there's 4 types of magnets: horizontal, vertical, correctors, quadruples, and sextuples. So now you just quadruple your number of inputs and outputs, but it's still a bit simpler. It might be easier to learn, and it might be able to answer this question of, will a magnet fail and will it fail at a certain time? And if you can reduce the search problem down to 4 magnets, that's still better than 1 in 1320. So that was some of the motivation behind trying to simplify it a little bit. So starting off with aggregating by the sector, here we're looking at just histograms of the data sets. These are scaled data using robust scaler, and just by eye, you can see that there are certainly some visual differences between the training data and the validation data, that's good. That means that there is something a little bit different about the sort of the anomalous data. So the autoencoder might be able to tell us whether or not we have anomalies. And then if you look at the difference on the right, it's a lot more clear where the differences are in the two data sets. But they're definitely apparent. And the training of the autoencoder is not for the 80 inputs and outputs. It's not that complicated. We get very good reconstruction of the data of the reference data set. As you can see on the bottom left, is the R squared for each of the parameters. And then on the right, you're just looking at, there's 4 or 5 parameters per plot, and you're looking at predicted versus the ground truth. So obviously it's reconstructing the data very, very well. And one thing I want to point out is that the encoder dimension I'm using here is 2, so and it's training very well, which is indicating that it might do an okay job of telling us whether or not a fault's occurring, but there's probably not enough complexity here to pick out which magnet it is that's faulting. And if we look at the reconstruction error, so this is the reconstruction error by magnet, and then the RMS reconstruction error for the entire ring. It's for each sector, sorry, aggregating over sector, just as a function of sample number. So the idea here is, if you're going to do if it's going to be totally unsupervised, then you need to set the threshold based on how well you reconstruct your reference data. So here you say, okay, if the threshold is based on RMS reconstruction error, then we would need to set the threshold to be about 0.6 in order to have none of the reference data be flagged as faulty. So then if we set the set the threshold to be that level, then how do we do on the test data set? And when we do set it low at 0.6, where there's essentially 0 data in the reference set that's being flagged as anomalous, approximately 8% of the data that was in the test set is flagged as anomalous. And 8% means sort of like 8% of the samples, and there's a lot of samples. It's not necessarily 8% of the magnets. It correctly identifies 16 out of 26 of the runs as having some anomalies. So each run has, anywhere between a few hundred to 1,000 data points in it, and the 8% of all of that data is flagged as anomalous, which means that during some of the runs, as you can see, there's sections that are anomalous and sections that are not anomalous. And in some cases, the whole run is anomalous, which is actually what I'm going to show on the next slide, I think. Oh, no, sorry. ROC curve. Yeah, so if you wanted to do it semi-supervised, you can just change, you would adjust this threshold and say, okay, well, at what point do I get all the true positives? And then what's my false positive rate if I have 100% true positives on correctly identifying anomalous runs. So in this case, you can get all of the runs to flag something as anomalous and only have a very small fraction of the reference data be flagged as anomalous, and then that might be better than incorrectly identifying or missing some of the faults. But the question about, can I tell which magnet it was that faulted? This is trying to get at answering that question. The short answer is no, not with this method with this particular simplification of aggregating by sector. And if we could identify an individual sector as being the faulty one, then you would see a nice single line for the sector number on the right here as being flagged. But in many of these cases, we're flagging numerous sectors as being faulty, which means it's just sort of not distinguishable which one is the anomalous sector, which is kind of unfortunate. But it also just means that there's more work to do to try other things. And we can play around with different metrics or different methods for, or even different simplifications, or use all the data, or use time domain type of predictions. And we're working on a number of those things. But for this particular study, we can't discern which sector it was that failed. But the good news is that we want to understand if the precursors do exist. So is there information in the data that tells us that a fault's going to occur? And in a lot of these cases, their precursors show up minutes or hours before the fault actually occurs. So in this case, on the bottom left here, there's one of the sectors is being flagged as faulty. It's not the correct sector, but it's a sector, and it shows up an hour and a half or so before the actual fault occurs. And that happens in a number of these cases. So that means that there are precursors that do exist that are at least different enough from the reference data that they can be differentiated with this type of analysis. So there's definitely some more work to do on this, but so far the results are encouraging. And then the next thing was, okay, well, let's go to magnet type in a sector. Obviously, it's a bigger data set. You have 320 parameters instead of 80. This is just the same data plot as I was showing earlier. It's a little harder to visually discern the differences, but if you look at the difference plot on the right, there's definitely some differences. So that's good. But the main thing I want to talk about here is the two different metrics that we're using for evaluation. So we can look at the RMS error, so that's the single aggregate parameter, or we can look at the squared error of an individual sector or an individual parameter and say, does the squared error fall outside of the threshold or not? And then flag it as anomalous based on either a single event or based on an aggregate event from all the data. On the right is just this is the fit performance of the neural net. So they're all reconstructing the data very well. One is for temperature data and one is for the current data on the bottom. Looking at current and temperature, it definitely has an effect, right? So if you look at these ROC curves, when we use temperature, if we look at temperature data, the false positive rate's a lot lower than it is for just looking at the current data. So that indicates that the temperature information is more informative in terms of identifying these faults than just looking at the magnet current by itself. And then in general, using RMS error as opposed to just a squared error is a better indicator of identifying whether or not a fault occurs. So that's interesting because if you want to predict which magnet it is that fails, then RMS error is not going to help you because it's aggregating over all of the different parameters. So that suggests that here we're more likely to succeed at just saying a fault's going to occur and we think it's going to occur at this particular time. So that's kind of what we're headed at next. Is we have the autoencoders do a good job of separating out the faulty magnet data from the reference data, and now it's how can we integrate that into something that can give us some kind of either like a variance on how far we are from the reference data, or how likely a fault is to occur in the next 10 minutes or something like that. So that's kind of where we're headed next with the work. And this is the same, the time domain prediction that I was showing earlier. This is now for the temperature on the left and current on the right. And I've separated out the two different qualification metrics. So in one case, we're using the RMS error. In one case, we're using just the squared error. And in terms of identifying precursors, the RMS error does better. But again, the RMS error is not that helpful when you're trying to pick out which magnet it is that fails. So we're still iterating on this, still working on trying to solve that problem, but at least we have a pretty good handle on the fact that we can use this method for doing some kind of analysis about whether or not a magnet, the ring itself is going to have a fault. So I wanted to just take a minute to thank the institutional support that we've had. There's been a lot of support from the APS. Michael Borland gave us all the data, and he's helped us with some discussions and just chatting about different things that we're interested in working on and trying to make some progress with this. And then Fermilab's also been very supportive of this work over the past year or so. And we had an SBIR with them that wrapped up over the summer, and the data was collected during last year's run. So appreciate the help from collaborators on this work, and we're looking forward to continuing it and hopefully making some more interesting advancements in the future. Thanks.